Hello there. I hope that this is better now. Good. So thanks very much to all of you who pointed out that there was no sound before, but I think we should be good now, right? Static and no sound? That's not good. Just a second. Is this any better? No, it's still static, right? Oh, so that is better. Double checking. Okay. So is there still a lot of static here? Or there's a buzzing sound you're saying? Or is this actually good now? Good? Okay. Great. All right. Well, thanks very much. Thanks very much to everybody for putting up with this as we got started today. This happens to be a collaboration that we're doing here with the InteGIRLS competition. And this is something which was based on a puzzle. This was a puzzle competition. Now, when there's... Oh, somebody's saying there's background music. Is that true? Let me see. There shouldn't be any background music. No, there's no background music here. A little buzzing, but good. So I just wanted to make a double check that somehow this thing is actually set up properly. The reason is because we were actually just using all of our filming equipment for something else, and that's why I wanted to ask. But if this is different from the way that it usually is with the rest of our streams, please let us know, because then we will be able to go back it. Okay, good. Right, so I'm very happy to have this collaboration, and this is a puzzle competition right here. And this puzzle competition was run by InteGirLS, and indeed it was, I believe, the competition was only for girls, but the problems are very interesting. Although I should actually say I didn't, whether competitions are for one group or for another group, I'm actually here just to talk about some problems. So this particular set of questions was one where there were a lot of puzzles where you looked at these and you were trying to figure out what these meant. So, in particular, I wanted to use this time to go over a few of their questions, which are actually quite interesting. This first one here is a puzzle that's written on the screen. What do you think? I don't know if any of you can read this. This happens to be a problem which is about trying to figure out what are these theorems. So these are all here on the screen, and this is a sheet of paper tucked away in your math textbook next to the page with all of the formulas. And so now, can anyone try to figure out what these might be? Let's see. Let's try to do them one at a time. The first one says, with the help of some square roots, Alice, Bob, and Carl were able to catch the 4 rats, fair and square. What theorem might that be? I see that some people here have interesting ideas. Jaden Tang says one of them looks like Pythagorean theorem. Actually, I'll agree. When I was looking at this problem, that was the one that I thought was the easiest of this whole list. I think you're probably looking at the second one. But the second one is about Alice and Bob and Carl are on vacation in Greece. Pythagorean theorem. The amount of square pasta that Alice and Bob had altogether ends up being the same as equal to the amount that Carl has. So I think that the answer to the second one is Pythagorean. The second one is Pythagorean. That was the easiest theorem that we're talking about here. So maybe I'll write that down here just to make sure that fits. Let's use a color that's easier to read. Hard to see that G in there. but let's pretend that's a G. That fits. So now if I've got that one in there, I guess the next question is, what should we do with the top one? I did see that there were some people here who got an idea for the top one. What's with the yellow? Well, you see, this is actually a puzzle contest. So we're going to have to figure out what to do with all of the yellow. What do you think you should do with the yellow? Usually what this means is that the letter that's inside on the yellow is interesting. Ah, Wu Ba Song, you're late. What's happening? We're trying to do a puzzle. This is a puzzle from the competition that we're collaborating with today. But this top one here is quadratic, because if you look at it, okay, I'll tell you, when I was thinking about it, I didn't realize that it was about quad rats. That was only afterwards. At the beginning, I was like, well, there's A, B, and C. How many equations do I know with an A, B, and C in them? And where there's a 4. I just thought of the quadratic equation because there was a 4AC, but I didn't understand why that would have anything to do with rats. Until afterwards I realized, oh, quadratic, quadrat. Ah, there we go. Let's see. So this has to be quadratic. Quadratic. Okay? So that one gave me an A. This one gave me a G. Now, what else can we do here? What other ones of these are maybe easier to get? I think that the one here took me a while. This one actually I think is fairly hard, but there's some of these other ones that you can actually put your finger on. Let's see. Well, I guess since I am sort of going in, should I go in order or should I not go in order? I won't go in order. I'll go and do this one next. I'll skip over this. This one to me is quite difficult. But the next one here, what else do we have? We have a problem here about before my death. I would like to say that my children, Alice, Bob, and Carl, will not get any of my money, no matter how many times they try. So it's by someone called Pierre. So it must be some French person's theorem. How many French mathematicians do you know? And I see Alice, Bob, and Carl. Usually those are A, B, and C. So I see people are saying, how many theorems are there from some French person involving A, B, and C, and like something about before this person's death? Oh, so it has to be something. Oh, and there's like a, what is that thing called? Apostrophe, right? And then there's some other letter. Usually after the apostrophe, it's apostrophe S. So it's someone's something theorem. Ah, I see. David Sia has a suggestion. Fermat's last theorem. Let's put that one down. I believe that is the correct answer. Fermat's last theorem. So that happens to be E. Okay. So in that case, what else do we have? Let's go to the next one. Gordon. Gordon is trying to organize his pantry by color, but he wants to see how many ways he can order red and blue items. By the way, I'm going to go and make this a little bit easier for me to read. So I clicked on something which makes it so that now when I look forward, I can see something much more clearly. Previously, I was always looking down because that was the only other way I could go and see. What could this one be about? So there's some Q here. There's a Gordon. Do you know any Gordons in mathematics? Gordon. And about ordering red and blue items, that feels like maybe it's permutations. Is that right? But it's going to be some things theorem, I guess. Well, if I'm ordering red and blue items, what else could I possibly get? I think, as I was thinking about this, yes, I see Derek Wang. Wow, you know this. This is hard stuff. So actually Gordon is the first name of a mathematician named Gordon Ramsay. And there was a Ramsay's theorem that's about red and blue things. And what I want to do with this problem is I also want to tell you a little bit about some of these theorems, right? So there also happens to be something called Ramsay's theorem. Ramsay's theorem, and that happens to be an S. And what Ramsay's theorem is about, Ramsay's theorem is like this. Oh, he's not the chef guy. Somebody asked us, isn't this like Gordon Ramsay? Oh, wait, you know what? Actually, you're right. Gordon Ramsay is the chef guy. But there was another guy called Frank Ramsay, and that's who this theorem is named after. But I think for most people in the world, Gordon Ramsay is the one who you guys would think of as associated with Ramsay. So the chef guy. But now, what do we know? What is Ramsay's theorem? Let me tell you a bit about what Ramsay's theorem actually is. Ramsay's theorem says that if you have enough people, all right, let's just actually talk about what Ramsay's theorem says, because that's an interesting thing to talk about anyway. I'm curious if there's more space here. Nope, there isn't. So let's do this. So if I want to say, here's an example of Ramsay's theorem. If I go and take any 6 dots, so I just drew 6 dots here, 6 dots. And if for every one of these pairs of dots, you either connect them with a red or a blue edge. So we'll just draw a bunch of reds. Let's call this red. You draw a bunch of reds. Okay, so for every pair, we'll either connect with a red or a blue. So I said for every pair. So that means that now everyone who's not connected by a red has to be connected by a blue. So I guess we do this. It's going to look kind of like a mess, but it's going to be worth it. Okay, so I think I just did these 2 vertices. This guy also needs to be connected to every other vertex, either in blue or in red. Okay. This one has to be connected to every other vertex, either in blue or in red. This guy has to as well. Are we done? Are we done? I don't know actually if we've connected everything. Does it look like we've connected everything? Here's the easiest way to find out. The easiest way to find out is to say that if you've connected everything, every single vertex should have 5 things coming out of it. So let's see. How many does this one have? 5 things. Good. And this one, 5 things. That one has 5 things. This one has 5 things. Counting is hard. This one has 5 things. Great. And the one in the middle also has 5 things. Yeah, so we've got them all. And what Ramsay's theorem says is that if you have these 6 vertices, no matter how you choose to connect them, there will always be a red triangle or a blue triangle. Or both. Is it true? Can you see a red triangle up here? I don't see a red triangle. But there's a blue triangle. Where's a blue triangle? Oh yes, there's probably a bunch of blue triangles. Like here's a blue triangle right over here. These 3 make a blue triangle. And I think these 3 also make a blue triangle. So Ramsay's theorem is saying that if I have any 6 of these vertices, no matter how I color some of those edges between them red and blue, there's always going to be a red triangle or a blue triangle or both. And now if you don't just want triangles, if you want to know, could I guarantee that there's always going to be a bunch of vertices where there's like 10 vertices and every pair is red? Or find a bunch of 10 vertices and every edge connecting them is blue? Then all you need is you just need to have like 4 to the power 10 vertices and you'll have that. So that's called Ramsay's theorem. It's actually pretty interesting. Is this a high school competition? A question already has come in. Actually, I don't know what is the exact level this is, but I'll say that for me, I think it's pretty interesting too. So let's see, what else can we do? Let's go to the next one. At a certain magical clinic, a hallway appears that seems to go forever. Investigations into the origin of this hallway come up indeterminate. What could this be? Meanwhile, unfortunately, my video feed of you guys actually just fell off. So I'm going to replug that so that I can see what you guys are typing. 1 second. Hello again. Okay, apparently what happened was that Windows needed to restart. So I'll be able to see what you guys are typing very soon. Thankfully, my moderators are still on, so if there's something that comes through, they will let me know. And I'll just continue talking about this one, right? So we have this certain magical clinic. What could this be? Well, I'm supposed to go and find some kind of a theorem or some kind of a fact that I could put here. But there are 2 apostrophes. How strange. If there are 2 apostrophes, you can't have like apostrophe S and apostrophe S again, can you? 1 second, the computer just restarted, so let me go and enter in. Great. So it's continuing to come in right now. And what we have here is that we have to have something that we could possibly put in. And what could you put in that will have 2 apostrophes? Well, at this point, you got to think, what kinds of things actually will have an apostrophe before anything? That seems to be that it has to be French again. So what else do you know? I've seen some French words where the first thing is like a D apostrophe. But is there anything else that might have to do with a magical clinic? What do you think? And maybe I actually already saw in the chat earlier, I saw that some people had suggested there's something from calculus. And the thing from calculus is this L'Hôpital's rule. Some people sometimes spell it L'Hospital's rule. L'Hôpital's rule. And this is a statement from calculus. That happens to be the I. So this happens to be a calculus theorem. L'Hôpital's rule, let me tell you a little bit about that, because it's not really that fun to just kind of say, oh, there are all these like famous theorems, right? So what's L'Hôpital's rule about? Well, I can say, sometimes you want to say, like, what's 0 over 0? I don't know. What's 0 over 0? Let's just use this space here. I just blanked everything out so that I can use some space here. Does anyone know what I should say 0 over 0 is? Unfortunately, I don't know. 0 over 0 is not something that you're allowed to do. Well, you're not allowed to do it because it's not clear that it means anything. But suppose I didn't have quite 0 over 0. Suppose what I had is I said, look, I'm curious about what happens when I take 3x over x. Does anyone know what this is? This seems reasonable. 3x over x, there's no question. 3x over x is just 3, right? Seems quite reasonable. This is 3. Except what happens if x equals 0? If x equals 0, you might say, you know, I can't really do 0 over 0, but everything else is 3. If x was 0.2, it's 3. If x was 0.1, it's 3. If x was minus 0.1, it's also 3. So let's just call it 3, even when x is 0. And that's the notion of what's called a limit. This is something that people will do in calculus. So now, that's where over here you might say 0 over 0 makes sense to be 3. Now let me try something else. 3x plus x squared. What should this be? Let's see. So if we happen to have x equals 0, it's still not good. X equals 0 is still not good. But you know, actually, when you have something which is really close to 0, this still has some reasonable value. Right? So what I'm saying now is like, what should it be when x is 0? That's the notion of a limit. If x gets closer and closer to 0, what should this get closer and closer to? And it should get closer and closer to 3 plus x. But, you know, if I'm saying x is getting closer and closer to 0, then this also gets closer and closer to just 3 as x goes to 0. Now, there's another way to think of this. Another way to think of this is that, you know, if you look at how this compared to just the 3x over x example that I started with, when you had the 3x over the x, then, you know, this 3x and the x, they were both kind of getting towards 0, but the 3x was getting towards 0 3 times as fast as the x was getting towards 0. And this x squared, the value, what x squared does when x is close to 0 is that actually x squared is insignificant compared to 3x. If you want to know what I mean, imagine that x was 0.01. If x is 0.01, then x squared is 0.0001, and 3x is 0.03. Oops, we already have a decimal. So if you can see, x squared is actually pretty small compared to just x. And so what L'Hôpital's rule is talking about, L'Hôpital's rule is saying, look, if I've got something over something, and for example, if it's becoming 0 over 0, what might be relevant is how quickly are they approaching to 0 on the top and on the bottom. It's like, what's the speed that the top and the bottom are approaching 0 at? And if the top is approaching 0 at 3 times the speed of the bottom approaching 0, then you should say that the fraction is something like 3. Does this actually make sense? I actually just talked about what L'Hôpital's rule without using the word calculus. So the L'Hôpital's rule is basically saying if I've got something over something and I'm curious about what happens as my x, for example, goes to 0, I could try to figure out the top and figure out the bottom. Sometimes it's 0 over 0, and oh no, that's useless. But you can also go and say, how fast is it getting to 0 divided by how fast is the other one getting to 0? And so if you talk about the speeds, then the ratio of the speeds of getting towards 0 is actually what this fraction becomes as x goes towards 0. I've actually just basically proved, well, not proved, proved is a strong word, but I've just explained the reason why L'Hopital's rule works. For those of you who are familiar with calculus, L'Hopital's rule says you take the derivative of the top and the derivative of the bottom and you divide. And this example shows what's going on. It's because the numbers themselves are getting close to 0 and getting close to 0. So what's relevant is how fast are they going to 0. And the ratio of the speeds at which they go to 0 is actually the limit of that fraction. Okay, so that was this L'Hopital's rule. I had to say it because there was this thing here. And that leaves us with one more. That last one is the hardest one for me. Does anyone know what that one is? That's actually pretty hard. I can tell you what I was thinking as I looked at this. So when I looked at this, I was like, what in the world is this talking about? Buying shoes? And what are Jordans? Oh, there are Jordans that curve. Aha. So there's actually a theorem in topology, actually, which is talking about Jordan and curve. This is something where Jordan curve theorem is a statement in topology that says if you just draw any curve, let's clear this up. There's something called the Jordan curve theorem where you kind of draw a curve and it's supposed to be a closed curve. So let's pretend it all comes back together. Then it comes towards, then you have something, and there's like an inside and an outside. That's what the Jordan curve theorem is talking about. So Jordan curve theorem tells you something about there's an inside and outside. And so what's going on here is that we have to have some kind of a theorem that has to do with curves. And there's also this temperature. So it turns out there's something I didn't know, and I learned it from this contest. It turns out that, so there was a theorem I was thinking about that uses curves, and it does fit in part of it. Stokes. This is now what's called multivariable calculus, so I won't actually go into here. So the Stokes part is part of it, and it turns out that the Stokes theorem is not just called Stokes theorem. It turns out it's called the Kelvin-Stokes theorem. So this is something that I also just learned myself. So that would be an N. Kelvin-Stokes theorem. And so this thing now gives you this thing now gives you like the complete thing that you need in order to finish out this problem. And we have these letters A-G-N-E-S-I. Agnesi. Does anyone know anything about Agnesi? What is Agnesi? Does anyone know what this is? Yes, and Kelvin as in temperature Kelvin. So it was a joke. Well, not a joke. That was the whole point of the puzzle. So what is Agnesi? So there is actually some history about who is Agnesi. Oh, Maria Agnesi. Right, because she actually wrote a handbook on mathematics. So actually, that happens to be maybe what this is about as well. So that was this problem. This is a pretty interesting bunch of theorems that are here, some of which are things that people learn early on, some of them are things that people learn much later on. But it's neat. Okay, what else can we do? So after discussing this book of mathematical formulas that Maria Agnesi wrote, let's see what the next question was that we wanted to talk about here. So the next question was about a pandemic. I guess there is a pandemic going on right now. You are a world-renowned epidemiologist, and the US government has just sent you an urgent transmission. Figure out the hidden message and report your findings to the Surgeon General's office as soon as possible. See next screen for the message. I guess I have to see the message. Oh, I'm not sure you guys can read this, so I'll do my best to tell you what's going on. So this says that there's a global pandemic, and the virus somehow only spreads between the hubs on this map that are on the next screen that I'm going to show you. And also the virus won't go between differently colored regions, okay? And then there's some pattern of transmission, which I'll explain as we get to the next screen. And it's talking about how from day to day to day, different people, different cities are getting this virus. And you're supposed to figure out the pattern of the outbreak. And after that, outbreaks have started out in 3 other zones, and you're supposed to figure out which cities are spared. And it says, since the beginning of the pandemic, the world has become completely mixed up. Somehow those things are bold. Wonder why? We'll find out. So this is the map that came with the problem. This happens to be, I guess, from a board game called Pandemic Board Game. And I'm not sure if you can read these here, but it's basically saying what's happening on each of those days. So the virus began in Seoul, Osaka, and Ho Chi Minh City. And then after that, then there's a few cities which got infected afterwards. Shanghai, Taipei, Tokyo, Manila, Jakarta, and which is this, Hong Kong. Right? So these are all getting infected. So the font might be a little bit difficult to read, but I'll just talk through as we're going. And this is saying, like, you know, after day 3, then there's some other cities that are infected, which actually got infected again. And then at some point, the virus stopped spreading through that region. And now we have to actually decide what happens in the rest of the world. For this, I need to actually look at a bigger map. So I'm going to start making some coloring as we're going. All right? So the virus began in Seoul, Osaka, and Ho Chi Minh City. So here's a bigger map. Seoul, Osaka, and Ho Chi Minh City. So Seoul is here, Osaka is here, and Ho Chi Minh City is here. You know, it's a little bit odd. When I look at this map, this is obviously the map from the board game Pandemic, but I have to say, I do travel in Asia sometimes, and the way that the cities are laid out is, I think, maybe more convenient for a board game and not quite accurate in real life. But in any case, what we have here is that let's pretend that this is where Ho Chi Minh City is, let's pretend that's where Osaka is, and let's pretend that's where Seoul is. For anyone watching from Asia, you're probably a bit curious about how Americans made this board game. In any case, so we got these things. And then after these are the first cities that got infected. Now we need to go and find out what happened next. What happened next is that some cities got infected in the second stage. Yes, those of you who are from Asia are probably a little bit curious about what's going on with this map. Okay. So if we go here, then the day 2 is Shanghai, Taipei, Tokyo. Oh my gosh, so many people. So Shanghai, Taipei, Tokyo. Shanghai. That's very difficult to read. I'm not sure you can see that's green. Let's just keep trying. We can use yellow. Shanghai. Oh, let's just go back to red. Okay, Shanghai, Taipei, and Tokyo got infected. And also Manila, Jakarta, and Hong Kong. Manila, Jakarta, and Hong Kong. I must say that the way that these things are actually put are not quite accurate for the map of the world. But again, this is what's in the board game. So we use what we use. So let's see. Is there any pattern for how, if there is an infection here, here, and here, how it goes to go into the next pink ones? And yes, the map the map unfortunately is the map from the board game, which is not exactly quite right. So this is not exactly meant to be a map. This is not a geography class, and you can see that when people made board games for people to play with, maybe they weren't so accurate on the on those city locations. So now, what's the deal here? How can you decide that those pink things get hit? Is there any relationship between the original white circles and the pink circles? Well, obviously, the white circles and the pink circles are next to each other, right? So it seems like it's clear. I mean, things go from cities to cities near them. But what's the rule? I mean, how come up here it went to these two, but not that one? Is there anything that you could say about these cities? Right? So somehow this one happened to be Seoul, and this one is Beijing, and this one is Tokyo, and this one is Shanghai. So you're trying to figure out under what circumstances does it not transmit. You know, like this one here was Ho Chi Minh City, and it did not go to Bangkok. Why would that be? Why would it be that you don't go to a particular city? Well, let's see. Maybe we can go and there might be something about, are there only 2 lines that connect it? Well, there's also something interesting. It says that on the third day, there's going to be some more cities that get hit a second time. So it's going to kind of bounce around, hitting other cities. And the fifth day, there's no more infection. I mean, no more new infections. So it's always kind of moving from city to city. Something interesting here is when you look at the problem, the day 3 cities are Manila, Taipei, Tokyo, and Shanghai. So there's actually a pattern. If you look at these, if you can read this, if you look at these, you can get an idea of, is there any kind of a pattern between the cities as we're going? So is there any pattern about these cities? Actually, these are puzzles. So the puzzles are designed to be things where, you know, you can go and play with it. You can try to find if there's any logic. And there's often weird things you can do that aren't necessarily just what you do when you look at the graph, when you look at the map. Spintop said there's something about alphabetical order. If you look over here, look, MTTS. Actually, at the beginning, you have the Seoul, Osaka, and Ho Chi Minh City. Then you have Shanghai, Taipei, Tokyo, Manila, Jakarta, and Hong Kong. Then you have Manila, Taipei, Tokyo, and Shanghai. Something strange. It's like they seem to be, the letters seem to be getting bigger. And that's actually the heart of the question. It turns out that in this particular question, the pattern of like what goes and infects what else is that it goes from a city to the nearby cities, which are bigger in alphabetical order. And that's it. So that's actually what's going on. So if you do this in one round, you start here, then the next round is the pink things, and the next round after that will just be the ones that are alphabetically one more, alphabetically one more, alphabetically one more, etc. And if we were going to do that, let's continue. So from this Jakarta, you will never get to Bangkok, but you will get to Sydney. And looks like you'll never get to Beijing. So if I look at this, what's going on here? Yes, indeed, there is somebody, Spintop Pro, somebody figured out what to do here. You can use the alphabetical part. So in this particular puzzle that they came up with, it would be that Bangkok and Beijing are the 2 cities that are spared, meaning that they were not affected. So now let me, on this right side, let me erase everything and just mark the ones that were spared. What's a good color to use? I guess white. I'll use boxes. So we have Beijing and Bangkok over here. And these are the 2 cities that don't get infected. Now we have to actually do the problem. So in the problem, what do we have? So we also have to say the next thing that happens is we have the black, inside the black region, Algiers and Chennai got infected. So Algiers is here, and Chennai is here, apparently. So these 2 are in the black region. And then what we do is we just do the same thing that we did before, which is we just go and have them infect the hubs nearby, which are with alphabetical order higher than that. So what we have here, we have my head in the way. That's what we have here. I'm trying to figure out the best place to go. I can stand over here. So now I'm over here. Right. So over here, if I have Chennai, where will Chennai's infection go to? It will go to Mumbai. It will go to Delhi. You see, all we're doing here is we're just going to the things that have alphabetical order higher. Mumbai will not go to Karachi. Meanwhile, Algiers goes to Istanbul. Istanbul, oh, it stops. Just a second. I think there's some more. Wait a second. I want to make sure I got that right. No, it does not go to Delhi. Chennai, oh, it does. That's right. Chennai went to Delhi. That's right. Delhi then goes to Karachi. It also goes to Tehran. Can go to Riyadh from there. Riyadh, looks like Muscat stays put, and looks like these are fine. So what I've just done is I've just gone and I've just selected the ones which are all with alphabetical order higher. Okay, so who's spared? Let's see. As we're looking at this thing. Yep. So who's spared? I'm just going to mark with a box. Okay. And now let's knock out all of the other ones. And it looks like we have quite a few cities which are spared inside this black Middle Eastern region, I guess, Middle East and South Asia. So what else happens next? So the next thing that happens is we have to see what's going on the other zones. So in the other zones, we have in the yellow zone Santiago, Bogota, Johannesburg, and Los Angeles. Santiago, Bogota, Johannesburg, and Los Angeles. Okay, so now I'm going to go back over here, so I'm not blocking. Yes, temp ID, the layout of the cities, unfortunately, I guess when people made board games, they had to make the board games so that people could put the pieces on them or something. So in that case, we will unfortunately have to just deal with the way that we have it in the board game. But now let's see what happens. From Johannesburg, J, and then the K is next. J, and then the K is next. Oh, and here's L. L can go to S. BO can go to BU, that's right. From S doesn't go to L, but Bogota does go to both Miami and Mexico City. So it looks like we have this one out here, L. Okay, Los Angeles is in the C, Miami is in Cuba. Well, you know, when people make board games, I guess they play around. Let's see, what do we do here? So these all clear out. So it looks like what we have left is just something over there. Okay, now I guess we have to do this last segment. What's in the last segment? Blue, Chicago and Essen. Wow, Essen made its way into this? Interesting. I didn't realize that that would be a city that would make its way into this board game. But anyway, Chicago and Essen. And then where will they infect? Chicago will infect San Francisco, Montreal, Washington, MN. Okay, that's right. NN, and then what is this? E for Essen. E goes to a whole bunch of them. P goes to M. Oh, L goes to M. All right, and it looks like St. Petersburg is just stuck up there, so that stays put. So St. Petersburg is not infected. Atlanta is not infected. Okay, so now we've gotten all of these things left. We've just figured out all of these cities which are not infected. And the question was just to figure out what to do next. Okay, so now what we have to do next is we have to go and figure out what we can do with all of these first letters, I guess. Is that right? What can you do with all these first letters? So here what we have is we have a bunch of different first letters to play with. So what do we have? Just a second. Day 4 is missing. What is day 4 is missing? Somebody told me day 4 is missing on my group. I'm not entirely sure what my moderator team is saying, but when we're saying day 4 is missing, I'm not sure what we can do here. In any case, let's continue, right? I just erased St. Petersburg. No, that's not okay. Let's put it back. All right. Thank you. I'm glad that this whole live stream here is watching. Now what are we supposed to do with the problem? So in this problem, we're supposed to say, let's go and report the countries of the hubs that will be spared. The countries of the hubs. Now I need to know where these are. So clearly, as you all know, this country called Lima is in the South Atlantic Ocean. Well, not quite. It's just that's the way that this particular board game decided to put it. We need to know what country is Lima in. I guess now I need to go and start writing all this down. So let's go in order. So Lima is in P for Peru. So that's Lima. What else do I have? I have this one here. What is this? This is Atlanta. It's in U for the United States. What else do we have? Where is this? So this is St. Petersburg is in Russia. What else do we have? What is this? Oh, Moscow. Also in Russia. Okay. What's this one? I have to look here. Cairo. That's in Egypt. Okay. What's this one over here? This one is, I can barely see it. What did I write a box around? Oh, Baghdad. Baghdad is in Iraq. Okay, what else do we have? We have, oh no, What is Muscat in? So there's a reason I actually know where Muscat is in. It's because around this time last year, I actually was flying to Saudi Arabia because I was also working with some of the people there who are doing Olympiads. And so Muscat, I believe, is in Oman. I think. Is that right? It's in Oman. I think Muscat is in Oman. And there's like some airlines that go through there. Speaking of airlines, there's a helicopter going overhead. Oh no. Now there's something I don't know. I don't have enough geography here. I cannot quite read that either. Salara? Does anyone know what city this is? I can't read it. I only did it based on the S. What city could that be? It looks like it's in Somalia, based on what I'm looking at here. But unfortunately, I actually can't read that. So... yeah, so I'm actually having a lot of trouble reading Salala. You're saying Salalai? Salala? Maybe it's Salala? Is it Somalia? I don't actually know where that is. So I'll have to say, oh, so there's two cities in Oman on the same map? So this is Salala. I think that's right. And unfortunately, we have people here who have the internet. And so what we're seeing, besides the car that just went by, Salala is also in Oman. Okay. Very interesting board game. They put two things in Oman. I love doing these questions with everyone here watching because you guys can all help me do them. All right. So we've just done all of these. We did Moscow. Beijing, I know where that is. That's in China. Okay. And finally, the last one is Bangkok, which is in Thailand. Okay, so I'm done. That's the answer. Wait, what am I supposed to do with this? Oh, something about mixed up. So it looks like they're all mixed up. Can anyone tell me what happens if you try to unscramble that? Whoa, we got some smart people here. So Ian Ray already has said, looks like Puerto Rico. It's like Puerto... oh, no, it's actually Puerto Rico, I think. This is not coronavirus anagram. It might actually be Puerto Rico, right? Is it? Puerto. And the second part is Rico. Cool. So these people here are pretty interesting. I'll say that whoever came up with these puzzles, you might say, well, who comes up with these puzzles? Well, it's actually pretty hard to come up with a puzzle like this. You know, if you wanted to come up with a puzzle like this, how would you do it? I'm actually really impressed. The reason is because, you know, they just found a pandemic board game. That's just a board game, right? And when people make a board game, they just put some cities down. To come up with the idea that you could have this kind of a way of spreading where you always go to the higher in alphabetical order, and then somehow when you look at those cities, if you write down the countries that they're in, you'd be able to come up with something that rearranges. That's really neat. I actually would never have expected that this is even possible. You know what I mean? Like if you wanted to come up with this puzzle, how would you do that? How would you even do that? You know, the amount of luck that comes from being able to come up with this with a rule that's so simple is insane. I mean, normally if I go and make a math problem, I can just go give you a problem and the answer will be whatever the answer is. But if you want to make a good puzzle has to be such that it looks natural, like the rules are not crazy. The rules weren't crazy. It wasn't like, you know, this one's going to infect randomly something else, which, you know, sometimes we use the first letter, sometimes we use the fifth letter, but it was consistent. You just used the first letter and went up in alphabetical order, and boom, the whole thing worked. I actually can't believe this thing worked out. That's actually pretty interesting. And that means that whoever came up with this is really clever. All right, so we're actually at 4:44. What I usually do whenever I do one of these collaborations with a contest is that I always want to leave some time afterwards, especially because there are people who might have come from the contest who might have questions. So I'd like to open this up to, you know, the way we usually run our Ask Math Anythings, which is that this is a chance for people to now ask anything. And if you are new here, you will now get a taste of what we normally do every single day at 4 o'clock p.m. Eastern Time. What we normally do is we have people start to ask random questions, and I go and attempt to figure out how to do them. Not just figure out how to do them, I also try to figure out how to teach something that might be useful at the time. So right here we have finished our celebration of the wonderful questions that InteGirls came up with. And now let's go and talk about other things that might be around your mind after having seen some of these. Does anyone have any questions? And especially if you're new here, feel free to ask. I see that there's a question about, how to prepare for AMC 10. I can quickly say something about that. AMC 10 is coming up in a year, so you've got some time. And I would just say that the best thing to do there is to go and make sure you're playing with some hard questions regularly. And definitely, if you want to find some hard questions, you can look at questions that came from before. But what you want to do is you don't want to just have someone tell you how to do them. You want to learn how to do this stuff by always trying to do things that are harder. Harder in the sense that you have to go and fight with it, not just have somebody else tell you how to do it. Cass Hood asked, is this the first time you've seen these puzzles? I did not solve these puzzles on the spot. Actually, I heard that these puzzles were really hard. And so since I heard these were really hard, I started to look at them in advance. So this is not like the other live streams I do. The other live streams I do, I actually just show up and I'm like, let's go and try to do some of these problems. And the reason is because math problems are problems where you usually don't have any lateral thinking or any of this surprising ideas that you would suddenly go and use. On the other hand, I actually wanted to play with them. So that's why, with the first question that I was talking through with everyone, the interesting thing was to go and decipher what clues these might be talking about for what theorems are hiding underneath. Shanika Farah has asked, or is it Farsh? I think it's Farah. Shanika Farah has asked, can we watch this afterwards? Yes. This, I think, will be kept up on the YouTube channel, and so you'll be able to watch this afterwards if you'd like. I understand that actually the competition is also going to have their Zoom live stream, which is discussing how to do the problems later too. So there's a question from Bingo 2019. There are a lot of OP people who work really hard. Are there any tips for being successful other than working hard? I'll say work hard and work smart. It's possible to just work hard and get nowhere. In fact, a very easy way to work hard and get nowhere is to decide that you want to spend your life practicing multiplying 10-digit numbers. If all you do your whole life is multiply 10-digit numbers by hand with pencil and paper, you will become the world's fastest person at multiplying 10-digit numbers. Well, actually you won't. I mean, you would hope that you could, but there are some people out there who somehow also do that, and they might even be faster than you. So what I'm trying to say is that you can always try to do some work, and if the work is not very useful, you just wasted your time. And so I think that the people who end up being really good are actually the ones who are always challenging themselves. So you should always be going to try to find some new challenge that you don't know how to do. And if you do that, then it will be the best use of your time. Other questions? I see some people talking about different countries. So we have people talking about overpowered. What's the maximum number of equal pieces you can obtain by cutting a sphere 10 times? Well, that's interesting. Okay, if you want to cut a sphere 10 times and you want to get equal pieces, the way I would look at this, I wonder if this is more tricky than the question about cutting with lines. Because actually this is a pretty neat question. So if you're going to cut a circle into some things with lines, the way you think about things for circles is you say every time I cut with a line, I've got 2 regions, and then I cut with another line, and when I cut with the other line, I get plus 2 more regions. Because what happened is that as I went cutting through, each of those regions made another one. And then somehow when I cut one more with a line, I can potentially get plus 3 more regions because I split 3 regions. And the number of things I split is basically the number of things that I pass through with my line. Now if I'm going to cut a sphere or cut space, it's the same principle. It's that I have a knife and I'm going to cut through. And my question is, how many times do I cut off a region? And if I'm thinking about this, the reason why this is now hard is because when you're cutting off a region in space, with the lines you could say, it's just that every time I cut through another line, when I go through another line, I could at most, like between any two lines, I could at most get another region. But for space, I'm not sure if I know the answer. Because space is more complicated. As you're going through, well, is it more complicated? Maybe not. Maybe yes. Maybe yes. And that's because you can have, for example, different planes. So I'll say I don't exactly know off the top of my head what we can do for the sphere. But I think that's a pretty interesting question, and I want to go and play with that. And the reason is because anything in 3D is more sophisticated than what you have in 2D. Yes, Leo, you're right. You want to count the intersections of two planes. But the issue is that somehow when you want to make regions in just in the normal stuff that I draw, I can just take two lines, and that's going to give me the boundary for a region. I guess it's also true with two planes, but weird stuff happens in 3D, where like in 2D I can go and make a shape like this. I can make a shape like this. Whereas in 3D I have all sorts of other angles that I could use. So I want to be a bit careful. The answer might be simple, but it's something one has to be more careful. It feels like it would be actually quite a bit more sophisticated. And that's just where I would need to have more in-depth thinking and drawing some more pictures. What else do we have? Other questions? Let me see. I also have some other things here. Okay. Shivan Dabi has asked, what math contest do you recommend for 7th graders? All of the ones that you can find. Nowadays you can do all these things online. And there are all kinds of different math contests which are online. You don't need to do a math contest to try to win. You actually just want to go and play with these things, just so that as you go and play with these problems, you get to practice thinking. Sort of like this one that was just here. This was pretty interesting too. And so whenever you find that, oh, there's a bunch of people trying to do some kind of a contest, well, go and join, and then you'll learn something from it. Bingo 2019. How do you solve extremely challenging problems? How do you get better the most quickly? You're the same person who was looking for, is there an easier way than hard work? You know, to solve these really challenging problems, I think that what you have to do is you have to actually go and sit there and attack them. And get used to attacking questions that are challenging. Like how to figure out what to do when helicopters keep flying overhead. But when you want to go and think about these challenging problems, I think that the main point is you want to be able to just sit there, fight with it, and not give up. And if you get used to doing that, then you'll get used to going and just hammering on a question until you're all the way through. David Jiang, any tips for online testing? That's interesting. I think given online testing, I can tell you a story of when I was doing online testing. This was a long time ago. But there was a time when we were supposed to write an essay, and you were writing the essay online. And that's when I learned the hard way that sometimes if you're doing an online test online, an online essay, if you press Control A, you know what it does? Suppose you've written an essay for half an hour. So you've written it into this big box, like the long essay for half an hour. Do you know what happens if you press Control A? What happens if you select, so you type for half an hour, you press Control A, and then just like, what if you press one more key? If you press Control A and press one more key, what happens? So again, you wrote an essay for half an hour, you pressed Control A, and then you just press any letter at all, and what it's going to do is it's going to select all, delete the whole thing, and replace it with the letter. So you're lucky you have Control Z. Actually, when I was doing this online test, the thing that we were using before was something made by the same company that makes the SAT. And they didn't have Control Z implemented. They only had Control A. And so there was no undo. So the biggest advice was absolutely do not press Control A. Because if you press Control A and you type anything else, everything gets deleted and there's no undo. Oof. Yes, it was bad. Fortunately, I experienced this on a practice exam. But my advice to you would be, don't rely on Control Z working. You never know if someday when you're playing when you're doing one of these online tests, you never know if they actually implemented Control Z as well. Uh-oh is right. So that's my biggest advice. Be very careful about the Control A. Other than that, like if you wanted to go and, do online tests better, I think best thing to do is just try not to get distracted by the screen and just try to do it as well as you can as if it was a normal test. All right, more questions. Oh, interesting. So Alan Liu is asking, should I grind Amy or math counts? And this question is about, should you spend your time going and practicing a lot of Amy problems or spend the time practicing a lot of math counts problems? And my general advice would be, it's whatever you are at the level of. If you find the math counts problems already to be reasonably easy, then go and play with the Amy problems. But if you don't, then go and spend some time working on those math counts problems. Like if the math counts problems are hard for you, that's fine. It's true for lots of people. And then just work on those instead. What other questions do we have here? I should say, if you're a guest here, if you're here for the first time because of the InteGIRLS competition, usually what we have is we usually discuss all kinds of random math problems and go deep into the math problems. So I'm just kind of looking at these different kinds of questions which are coming in. Although here I have been also answering very general questions as well. I'm looking to see what kind of what the variety of questions that we have here that we can pull out. I see that Judy and Andy is asking, what was the programming behind Novid? Was it difficult at times? Yes, it was. And that's actually what I'm always working on right now. That's one reason why these live streams sometimes start like a minute late, because I've been going straight from a computer into doing something. But some things about the programming that you might find interesting is that there are, for example, some things inside computer languages where if you write them in certain ways, they can be 100 times faster than other things. It's like if you write what's called a for loop. In certain computer programming languages, if you run a for loop, it can actually try to do each of those lines. It's like, okay, what should I do here? What should I do here? What should I do here? It thinks, and it's like 1,000 times slower than what it could be. And instead you can try to run other commands which will do the same thing as the for loop, where it doesn't have to keep checking, what's the instruction for me to do. It's as if you gave it a bigger instruction and said, just go do this for a while. And that's what I've been playing with. What else can we have here? I see that Ethan Gung is asking, at exactly what distance would the sun have to be from the Earth so that we would be instantly killed? Well, the key word is instantly. I'm not really sure about what you need for instantly, in the sense that somehow, if we were just twice as close, let's talk about this. Like if the distance from us to the sun was half of what it is, that the amount of radiation we'd get, it would not multiply by 2. Radiation goes with what's called the inverse squared law, in the sense that if you go twice as far, the radiation is 1/4. So, for example, if we went and got, half the distance to the sun, then we would have 4 times the radiation that we would have right now. And if you think about the way the sun is, it's like, how bad would 4 times the radiation be? It'd be bad. It wouldn't kill you instantly. But on the other hand, it probably would start to give you a little bit of sunburn. That would not be very good. And in the longer term, it would make the Earth too hot. In fact, the Earth happens to be in a very, very just right radius from the sun to be what's called the habitable zone. Too close, and it gets too hot. Too far, and it gets too cold. And both of them are bad, because we all need to have just right. So, actually, even if you moved half the distance to the sun, and you got more sunburn than usual, the worst thing is that you just get too hot of an Earth. If you want to talk about instantly, I would say probably if you took the sun's radiation and multiplied it by like 1,000,000, that would probably be bad enough, right? And the way I'm thinking of that is because when you go outside, you put on this SPF, like sun lotion, and the SPFs only go up to about 30 or so. And so if you suddenly went times 1,000,000, that's probably pretty bad. And for times 1,000,000, you just need to get 1,000 times closer to the sun. And so that would probably be pretty bad. Okay, more questions. What else do we have here? Okay, let's finish with one thing here, which is, again, it looks like we're using this live stream, since we did a lot of these puzzles already, we're using the rest of this live stream just to talk about these general things about learning. And Shanika Farah asked, do you have any advice on how to prepare for Precalculus? Or do you have a video every day at 4? Well, those are different questions. Let me start with the first one, which is advice on how to prepare for Precalculus. I don't think you really need to specifically prepare for the Precalculus you take at school. I think that if you in fact go and just learn how to think about interesting math problems, like what we actually typically do on this channel or on the courses that we run, on that you would actually be able to learn a lot about how to think, and then Precalculus would just end up being pretty easy. In general, you shouldn't really need to prepare for a school course using the summer. Instead, you can use the summer. Don't just learn the course ahead of time. Use the summer to really learn how to think by working on things that are like puzzles, like what we talked about today, or challenging math problems that are puzzles in themselves, where you don't know what to do when you start. And so that would be my advice to you. And then you don't need to do any specific preparation for pre-calc. But you should do math in the summer. That would be a good thing to do. Just do interesting hard problems. And the question of do we have this live stream? Well, we currently do have this live stream every day at 4 o'clock p.m. Eastern Time for 1 hour. And usually the live stream does not consist of somebody else's puzzles. Usually it's the kind of direct math questions that people ask from the audience, and I just go and try to teach something on the spot. And we'll be doing this, for as long as I can. And I want to make sure I make that statement clear. It's that I love to do this. But as many of you know, I'm also working on a lot of other things, like this Novid app to try to actually stop the spread of COVID-19. So to the extent that I have time to continue doing this every day for an hour, I'll be happy to. And with that, I want to thank everybody who came for this collaboration. It was very nice to meet you and to see the new people who came in today. We will go back to our usual programming tomorrow, where it's Ask Math Anything. Come with whatever questions you have, and we'll go and try to figure out a good answer to give you. Until then, I'll see you all later, and I wish you a very good day.